Hey everybody, Mr. Piercy here, and in this video what we're going to be discussing is congruency between triangles. Now, the idea of congruency, if you look up a definition of it, the congruent figures literally have to have the same size and same shape, meaning everything about them from one figure to the next must be identical. And so what we're going to do is we're going to justify whether figures, in this case triangles, usually, are going to be congruent to each other because we can show all of their sides and all of their angles are the same. Now, one of the things that we need to be able to identify are corresponding parts. The way figures are named in geometry is relatively important when we're comparing them one to another. So looking at the notes that I've added on the left side here, we have two triangles. We have triangle ABC and we have triangle DEF. Now the reason why I'm calling the second triangle DEF is because of how I named the first triangle ABC. Because I started with A, looking at the diagram, it has the two hash marks. And from A, I went to point B along the side that has a single hash mark on it. Then I went along the side from B to C that has the three hash marks on it, and then finally back to A to close it. So in order to identify the corresponding parts properly, I have to name the second triangle in the exact same fashion. So you can tell looking at these, they're not drawn in the same orientation. And the D got cut off a little bit here, but there's point D. So because I started at the angle that had the two arc marks on it, and I went down the side that had one hash mark on it to the angle that had a single arc on it, I have to start at D, then go to E. And then we can go from E to F, and then finally back to D. So that's how we named it DEF. If you don't name it in the appropriate order from figure to figure, you're going to misidentify what your corresponding parts are. In fact, as long as things are named properly, you don't even need to see the figures in order to know what they are. So let me just cover this guy up here real quick. So let's just cover this up so that way we can't see it anymore. I probably should have picked a rectangle instead of a square. But so looking at the triangle ABC and DEF, the way that congruency statement is written, we can just look at the figures themselves, or at the names themselves, I should say, to show what sides correspond to each other. So for instance, if I say CA, segment CA, and I want to know what segment corresponds to it on the other triangle, all I have to do is look at the order of the letters. I said segment CA, which is the third letter, then the first letter. So the way I will name the second one is with the same way. I will look at the third letter, then the first letter, so I would say FD. Okay? So pay attention to how you're naming your figures, put them in the correct corresponding order, and everything should be okay. Now, again, if we want to be able to show that triangles, or really any figure, are congruent to each other, ultimately what we need to be able to show, it has all of the same corresponding parts. All of the sides, all the angles are the same. And one of the things that you're going to be challenged with is identifying things that are not drawn in the same orientation. So looking at the figures here, triangle ABC again, well, how would we name triangle ABC based on what we see? Well, looking at the figure, they're not drawn in the same orientation, just like the other ones weren't. Looking at A, I'm going to go to B. So I'm starting at the right angle, going along the side that has two hash marks to angle B that has a single arc. Then I travel along the hypotenuse that has three hash marks on it to point C. So I'm going to follow the same pattern on the other figure. So I'm going to start at the 90-degree angle, and I'm going to travel along the side that has two hash marks to the angle that has one arc on it. Then I travel along the hypotenuse that has three hash marks on it to point H. So the way that we would have to name the second triangle would have to be triangle FGH. Oops. I guess it would help if I took it off of the pen and turned on the pointer. So triangle FGH. Now that we've named the figure, we can either use the name of the figure, the corresponding triangles ABC and FGH, or we can go and look at the figures to see which angles correspond to which. So looking at the angles, we can show that angle A and F go together, B and G go together, and C and H go together. Same thing with the sides. If I say side AB, I have to say side FG, and so on. Now, in the example that we see underneath, we're talking about we have a quadrilateral. Now, this quadrilateral, there's nothing really unique about it. There's no special sides, like none of the four sides are really congruent. No angles are the same. No sides are parallel to each other. That type of quadrilateral has a name. It's not something that we actually see very often. It's called a trapezium. And in this quadrilateral, we have QRST being congruent to WXYZ. Now, they're not asking you to prove that they're congruent. This problem is setting it up saying, well, these things are congruent. So as long as you can identify the corresponding parts correctly, you can tell, well, what are the measurements of some angles and what are the measurements of some sides if you need it. So find the value of X and Y. Looking at the figure, we can see that the second quadrilateral, the one in the bottom, has X at angle W. So either looking at the figures or looking at the names, I can say that angle W and angle Q correspond to each other. And because the figures are congruent, those angles must be congruent also. So we say angle Q must equal angle W. Substituting their respective values, we're going to get 65 is equal to 5x plus 5. Move the 5 over through subtraction, and then divide by 5 to get x by itself. So consequently, we could do the same thing for solving for y. Now, unfortunately, where y is on segment WX, we have to be able to figure out what x was first, because it does say y minus x. So now that we know what x is, we can use that. But first, well, what sides go together? Looking at the figures, we can say that WX must correspond to QR. So since they are congruent figures, or corresponding parts of congruent figures, their measurements are the same. So we can say 6, the length of QR, must equal y minus x. And now that we know that x is 12, we can substitute it and say y minus 12, move the 12 over through addition, and get y is equal to 18. So at this point, I want you to go ahead and pause the video and answer these two questions on your own. Read the instructions, what it's asking you to do, and when you're ready, hit play again so you can compare your answers against mine. Okay, so question number 1 is simply asking you, identify the corresponding parts. So we have to identify the corresponding angles and the corresponding sides. Doesn't really matter which one you do first, but you do need to make sure that you do both. And you can do it really, you don't even need the pictures because again, looking at the way that they're named, quadrilateral FGHJ is congruent to quadrilateral STUV. We should be able to just look at where those letters are in their names to identify what angles go together and what sides go together. Or you could just look at the picture, whichever works. So looking here, the angles that correspond together are F to S, G to T, H to U, and J to V. And here, the segments that go together. Now looking at example 2, find the value of X and the measurement of angle G. Well, because the figures are corresponding to each other and they're congruent, angle G and angle T have to be the same length. So we find that, hit those in the wrong order, G and T have to be equal to each other. So we say 2x minus 7 is equal to 103. Solve for x and we get 55. Substitute it back into the expression for angle G, and we show that that measurement also is 103 degrees, which is exactly what we should see. Now, what we're looking at here, this is kind of an example of where they're trying to say, how can we apply this to something beyond maybe in just the classroom? So here we have a map, it looks like a map of Australia. And what they're doing is they're basically telling you, well, we've created a rectangle around it because they're saying the opposite sides are parallel to each or are congruent to each other, and we have right angles. Then basically they're telling you that we have a rectangle, and they're drawing the diagram or the diagonal from P to R, so they're really cutting it into two triangles. Well, what we want to know is, are those two sections of triangles, are they the same size and the same shape? Now, we've been practicing with a lot of two-column proofs, and this is an example of a paragraph proof. Now, personally, given the choice, a lot of times I really will go with a two-column proof because a paragraph proof and a two-column proof really do contain the same information, but sometimes paragraph proofs take longer to write because when you're explaining things actually properly in English, you can't get away with some of the shortcuts that you do in a two-column proof. But I digress. This is the most intuitive way that students are going to be able to do it, so if it works, go for it, use it. Now keep in mind, in the two-column or in this paragraph proof, none of this is given to you. All you're doing really is just filling in the blanks. They're kind of giving you the structure to work with, and you have to fill in the blanks as you think about it. So if you're going to write your own paragraph proof, you will ultimately be generating everything that's there, not just filling in blanks. So in the diagram, we can show that angle S is congruent to angle Q. And we know that because every right angle that we ever see in Euclidean geometry is always going to be congruent to each other. And so by the perpendicular to a transversal lines theorem, PQ must be parallel to RS. You know, makes sense. If we have two lines perpendicular to the same thing, then they have to be parallel to each other. So that means the measurement of angle 1 must be congruent to angle 4, whatever that is, and angle 2 has to be congruent to angle 3, and that's because, well, alternate interior angles are congruent when you have parallel lines. So all of the pairs of corresponding angles also have to be congruent to each other for the same reason. When my lines are parallel, the corresponding angles are the same. So that means that the diagram shows that PQ has to be congruent to segment RS, and that QR has to be congruent to segment SP. So the reason why we say that is because of the reflexive property. I'm sorry, getting back up, I'm not reading it properly. What we're saying is that PR is congruent to RP. That's the reason why we're using the reflexive property there. So that means all corresponding parts, all of the sides and all of the angles are congruent. Therefore, the two triangles have to be congruent as well. So we are able to say if the triangles are congruent, they will have the exact same size and the exact same shape. So moving on, what we're going to be looking at is something known as the third angles theorem. Essentially what that's saying is that if you have two triangles where two of the angles of one triangle and the same two corresponding angles of the second triangle are congruent to each other, well, their third angles also have to be congruent to each other. And that works whether the triangles are congruent or whether they're similar. Because angles, if I have three angles congruent in a triangle to another one, that doesn't mean that the triangles are the same, that just means that they're similar. But this still holds true. If two angles of one triangle are the same as two angles of another triangle, then the third angle also has to be the same. So here, find the value of the measure of angle V. Okay. So looking at the diagram here, we know we have some angles that are the same. Here, we know that this has to be 66 because they're marked to be congruent. And here, angle VUW and SUT, those are congruent, and I should use more than one. Those have to be congruent because they're vertical angles. So the two angles that we see in the two triangles are the same. Therefore, the third angles at S and V also have to be the same. So there's a couple approaches you could have taken to figure that out. But that's really kind of how we're going. So we would just say 180 minus the 44 minus the 66 to show that the measure of angle V is going to be 70 degrees. Now here, this is going to be something that you guys are going to be seeing a lot of in the coming topic here. We're going to be doing a lot more two-column proofs. Now, as you start doing this thing, when you first start with proofs, it is a little shaky, and I'm not saying that it's ever really going to become super easy, but when we use two-column proofs with triangles proving congruency, a lot of times this is where students start to get their legs under them when it comes to proofs. So if you've been struggling up to now, ideally, historically, the stats show me that this is where you're going to start to get a little bit better at it. So what we're looking at here is take the given information and we want to prove that the two triangles are congruent to each other. Now the given information has really already been marked on the triangle itself. So corresponding angles and corresponding sides that were given to us have already been marked congruent to each other. So what we want to know, or what the only thing that we would be able to include is that this side here, HG, well, because that's shared between the two triangles that we're trying to show congruent, well, that has to be one of the things that we want to conclude in our proof. And the only other thing that wasn't really marked for us was F and J. We have to be able to show that those are congruent. But if we know two of the three angles in a triangle, we can figure out the other one by the third angle's theorem. So the first thing I'm going to do is naturally take the information that was given to me and write it down. Then I can say that the third side is congruent because of the reflexive property. So in the first two statements, what we've done is we've shown that all of the corresponding sides of a triangle are the same. Well, what about the angles? So again, two sets of angles were given to you. So all you need to be able to show is that the third angle, F and J, those are congruent by the third angle's theorem. Therefore, the two triangles are congruent simply because, well, that's the definition of congruent triangles. Right? Doesn't even need to say triangles, that's just the definition of congruency. If all of the sides and all of the angles are the same, then the figures have to be congruent. Now here, this is going to be something that we're going to be using in our proofs. The words that you're seeing here, the reflexive property, the symmetric property, and the transitive property of congruence. Basically, this is saying is that for the reflexive property, if you have a triangle ABC, anytime you see the triangle ABC used in a figure, well, it has to be congruent to itself. So that's the reflexive property. It's kind of like saying, well, it's shared like the sides or that angles are the shared in the same thing. Well, if a figure uses the same triangle and another figure uses triangle ABC, well, it has to be congruent in both figures. The symmetric property of congruence is really when you're just kind of taking the figure and saying, well, if this is congruent to, if ABC is congruent to DEF, all we're really doing is just reversing the order of the congruency statement. And to be quite honest, the symmetric property of congruence, this one isn't going to be one that you use a whole lot of. The reflexive property and the transitive property, those are going to be things that you'll see much more commonly in the proofs as we move forward. So the transitive property, again, that's really kind of like, you know, the law of syllogism that we had in our logic unit, where we say if triangle this is congruent to triangle that, and triangle that is congruent to triangle what's it, then triangle this has to be congruent to triangle what's it. So ABC is congruent to DEF, and DEF is congruent to JKL, then that means ABC also has to be congruent to JKL. So what I'd like you guys to do here is go ahead and just, again, just like normal, pause the video and try and answer these last three questions and see what you come up with. And when you're done, hit play and compare your answers to mine. Okay, so let's see how you did. So looking at the figure here, what I'm going to say is I'm going to take the information and I'm going to start marking stuff down so I know what I can use. In the diagram at the right is the midpoint of AC and BD. Well, it's the midpoint of AC, AE and CE have to be the same length. And if it's also this midpoint of BD, then from B to E and from D to E, that has to be the same as well. Now looking at the fact that we have lines that are parallel to each other, we can say angle A here and angle C here, those have to be congruent because they're alternate interior angles with parallel lines. And here at point E, we have some vertical angles that are the same. So there's 2 out of the 3 angles, and if 2 out of the 3 angles are the same, then the third one has to be the same by the corresponding angles theorem. I'm sorry, the third angles theorem. So that's how I wrote out my answer as a kind of a paragraph. Looking at number 4, in the diagram, what's the measurement of angle D? Well, again, we're kind of looking at the third angles theorem here. So B and C are going to correspond to each other. And E, at point E, you do see that we have a couple of vertical angles. So all we're really going to do is we're going to say 180 has to be subtracted by 71 and 47, so the measurement of angle D has to be 62 degrees. And the last one, by the definition of congruence, what additional information would I have to know for the triangles to be congruent? Well, I also have to know that I have the remaining sides are the same. So that's what we would have to show that those are congruent to each other, to show all the sides and all the angles are the same. So that's pretty much it for this lesson. So just as a quick recap, corresponding parts, make sure you line them up properly when you're naming one figure to another. Because we're showing that we're trying to say that things are congruent to each other right now, we need to say that the only way we will accept congruency is to say all of the sides and all of the angles are the same, so you have to be able to justify it in some way. And if you have any questions, again, just like always, let me know. Send me an email, leave me a comment in the classroom. I'll be happy to work with you on whatever questions that you have. But until then, guys, good luck with the assignment, and see you later.